we will continue with the yarn evenness. Okay. Now, so we will discuss another ways of expressing the yarn unevenness. It is the imperfection. Imperfections are basically are the staple yarns at a number of places along with their length contains large variation in mass per unit area. So, any staple yarn if we produce, so there will be inherent defect in that yarn which is actually inherent part of the yarn. Okay. So, that it is due to the problem in the technology, okay, problem in the machine. Okay. There we cannot have a yarn staple yarn without any imperfection. Only thing we can reduce the intensity, reduce the number of imperfection. There will be definitely some thick places, thin places or naps. So, thick places there will be little bit more number of fibers than average, there will be less number of fibers in the cross section than average, or there will be some knot type. So, the difference between thick place, thin place or naps are classified based on the diameter or mass per unit length proportion of increase or decrease as compared to the with reference to the mean value. Now, this the imperfections are inherent nature of the staple yarn. I am emphasizing this inherent nature. Nature means this has to be there. We cannot have any yarn practically, theoretically it is possible, in practically without any thick, thin or naps. There has to be there, because this is the nature of the production line, and these causes are due to defective raw material or manufacturing process. So, this will be there, but we can reduce the level, and the thick places are example for say 50% thick place, 50% level. So, what we calculate? We calculate the number of thick places, number of places where the mean value is plus 50%. It is actually thick place, thin places are expressed in terms of plus or minus. Plus 50% means the mean value, if we talk about the 100 and then plus, that means 150%, that means 50% more than the mean. If the counter is actuated, the mass per unit length, that is cross, it is proportional to cross section. If we assume the packing density same, at a thick place is 150% or more of the yarn value, yarn mean value. So, it should be 150% or more value, then we will call it as thick place, but in thick place there is another condition, the length should be more than 4 millimeter length. So, if it is less than 4 millimeter, it will be considered as the naps. Now, the naps in the capacitance principle, the naps are counted based on mass. Okay. If even if there is no change in diameter, if the mass per unit length is higher by say 100%, so double, if it is double, and if its length is less than 4 millimeter, then it will be called as the nape. But in diameter type measurement, where it says that rate of increase in diameter, if the rate of increase in diameter of yarn, this is the yarn, then if it is high, then it will be called as the nape. If the rate of increase in diameter is slow, this angle, if it is less, then it will be called as the thick place. But the length is always there, the napes will be less than 4 millimeter. If it is longer, then it will be called as other type of parameter, that it will be called as faults, that we will discuss later. So, napes thick place is more than 4 millimeter, and range, typical range is 100%, 70%, 50% plus 30%, 35%, it is typical ranges, but one can have 60% also, any range one can have if we have data, it is matter of only software. Okay. Thin place minus 50%, so only 50% of yarn mean value or less. So, any value less than or more 50% or more, then it will be called as thin place. The different ranges are there, 60, 50, for 30 and minus 30%. So, these are the different ranges, and this will be actually cumulative value. So, means that plus 35% or say plus 100%, it takes care of all the value, rest are other values also. Napes plus 200% napes plus 200% napes means it is the total mass per unit length will be 300% of the mean value. That one must be very careful, like 280% nape means the mass per unit length is 380%, okay. That means plus 280%, and its reference length is 1 millimeter. Shorter length, that is less than 4 millimeter, but it is actually specified as 1 millimeter length. Now, coming to one of the most important diagram or most important actually method of measuring the technique of measuring the periodic fault, the spectrogram. Spectrogram only talks about the periodic fault. If the yarn, if the material does not have any periodic fault, then spectrogram will not show anything. Okay. So, the amplitude of this periodic mass variation is plotted against the wavelength in the spectrogram. So, in x axis there will be the wavelength of the only the periodic fault, that is I am just repeating, it is only talks about the periodic fault, not any other fault. Okay. Now, the amplitude is it is not the amplitude we have discussed the variability, it is the amplitude means here the number of times a fault of that repeat length occurs. It does not talk about the extent of irregularity. Okay. It actually the spectrogram does not talk about the extent of irregularity. Okay. From the speed at which the yarn is run through the capacitance type tester, the frequencies are converted to wavelength. Okay. That is the frequency, that wavelength is converted and plotted into a finite number of discrete wavelength steps. Okay. Now, suppose typical wavelength of cotton, sorry, spectrogram that this is the typical wavelength of this is the, and say very uniform yarn. So, this is the very uniform yarn. Now, if we have a yarn with high u percent, very high u percent, suppose this is a yarn, very even yarn, fine, very even yarn, and another yarn with very high unevenness, then how the spectrogram will look like? The nature of spectrogram will be exactly same. Spectrogram does not take care of any random variation. Okay. Now, suppose there is a yarn with a very nice. Now, here what it will do, from the data capacitance value data, it will immediately it will get the value of the wavelength from the speed and capacitance that from the speed, it will immediately identify this is the wavelength. This is the wavelength, it is taking place. Here every periodic fault, it will start plotting, this is a baseline, this is the baseline, it will start plotting the number of times the periodic is occurring. Now, if the periodic length is smaller, shorter, variation is there with shorter length, that means it will immediately shift this here somewhere, and here number of times it will start from this point. There are some adjustments are there, but one will always we can see the larger wavelength. So, if the wavelength is say further high, so number of times it will occur, it will show with a smaller, but meaning here is almost same. Here the height of hump will be, chimney will be little bit high, because here we have more number of data, because more here although less number of repetition. So, if we get this value with small chimney, that shows that there is a periodicity at that wavelength. This is wavelength. Okay. At that wavelength there is a periodicity, but although as our test length is say 400 meter and this may be say 100 meter, within that test length only 4 times it could happen. Now, whether this is significant or not, or whether it is a by chance it is taking place, that you can judge by comparing this height and this height, the ratio of this height, that shows whether it's a significant or not. If you have any doubt, the ratio is okay, because as you are going higher side the ratio will remain almost same, but still if you have any doubt, what one can do, instead of 400 meter speed, meter per minute speed for 1 minute, you run the same yarn for 10 minutes. So, you have got, so say 4000 meter. Then this periodicity, this and this total length will be, instead of say it is a say 1000 meter, here you are getting something, so or say 400 meter, it is 4000 meter. Now, this will be shifted somewhere else, the wave this will be readjusted, then here somewhere else say it is a 400 meter, or here somewhere else it will be 400 meter. Then you will have number of data, and then for this, as it is shifted here, it will give you certain chimney, and this chimney then you will say it is a significant. Now, you are sure that the problem is somewhere else, the same problem. Now, this is showing the periodic fault, but what about this base? Base is nothing, base is actually it is a equation, it is nothing but a equation. It is a, if you run a filament yarn perfectly uniform, you will get something this way, that is the basic base. It does not talk about the variation, only the chimney, only this, any periodicity fault occurs, then only it will calculate the wavelength and number of times it is occurring, then it will keep on enhancing. It is actually above that curve, that is the spectrogram. So, basic spectrogram is a equation, just nothing but an equation, and it is a histogram which is plotted automatically, okay, and the plotted into finite number of discrete wavelength steps, okay. And that we have discussed. If we have any doubt, if you have identified any small peak and you are not very sure, always it is done, you increase the test length and try to test it. If at all there is any variation, any periodicity, it will come up, it will show up. So, it helps in locating the generating point of a periodic fault. It will never tell any other fault. If the machine is generating periodic fault, then spectrogram is useful, otherwise it will not give anything. Spreading of hump is also there. Now, this we may get sometime. In addition to this, suppose it is nothing is there, okay, and no clear chimney is visible, it is there, and what we are getting? We are getting cluster of chimneys, small chimneys. These are basically due to the drafting wave. Drafting wave to some extent, although it is a random in nature, but it has been observed that problem in drafting zone, mainly in main drafting zone, it actually generates periodic fault, and that it shows up in the spectrogram. As I have mentioned, spectrogram only shows the periodic fault. So, in drafting zone, drafting wave, its spreading of humps are due to periodic faults generated due to drafting wave, and it has got certain wavelength which is typically for cotton 2.5 to 3 inch. So, if we think that cotton mean length, it is a 2.5 to 3 times of the mean length, that is for cotton. So, within 2.5 to 3 inch we will see if there is a cluster of humps, okay, spreading of humps are there, then we must be careful that there is some problem in drafting wave. So, either we have to reset the draft zone setting, or we have to see that whether there are short fibers are there or not, or something else, or maybe the apron there is a problem. So, drafting wave is mainly due to this short fiber, and that we can identify by the spreading of humps. Now, this is the periodic fault here, this is the normal curve, okay, normal for normal cotton yarn without any periodic fault, it is there, okay, and it does not show, it is very clear, it does not show any its level of uniformity. Level of it never shows the level of uniformity, it shows only periodic fault, and period, it is important because we can actually the periodic fault, as we have seen, it creates major problem in appearance, and we can, it is basically due to some periodic defect which occurs in a particular machine, okay, and these are mainly due to the eccentricity of roller or some broken teeth like this. And this here, this is the zone, initial zone 2.5 to 3 inch zone. Here if it is there, it shows there is no such hump, that means there is no problem of this yarn with a wavelength, drafting wave problem is not there, but there is specific, definitely there is a periodic fault is there at this wavelength. So, what is the wavelength? If it is basically it is a 100 centimeter, maybe say 1.5 meter or 2 meters in logarithmic scale sometime. So, at that length it is a periodic fault is there. Now, theoretical spectrogram, as I have mentioned, it is a curve, this is the curve, this is the curve, this is the function of this is the lambda which is wavelength, and this is the equation which shows the n is the number of fibers in the cross section, L is the fiber length, and lambda is the wavelength. So, if we plot this, we will get this type of curve. This is the, if we simply plot this equation, this is the type of curve, and for man made fiber where the length, number of fibers and length of the fibers are fixed, for constant length, L0 fiber length, we will get this type of plot, and this is the 2.5 L, which is actually shows the position of the drafting wavelength. Okay. But for cotton, where the variability is there, variability in the fiber length is there, the typical curve is like this. This is for natural fiber, like cotton we have this type of length, and here this is at this point we get this is due to the variation of that periodic variation of the drafting wave. So, 2.5 to 3, okay, 2.8 to length, this is the at where automatically it will give the highest hump. Okay. Now we will try to see few practical problems, and what is the implication of how to use the spectrogram, what is the use of spectrogram. Now, figure here it shows 3/3 drafting system, 3/3 drafting system, and it is producing 40 NE cotton yarn from 1.212 NE roving with a break draft of 1.115. So, break draft here between back roller and middle roller 1.115 break draft. Identify the position of peak in the spectrogram. So, what will be the probable position of the spectrogram if the pinion D, which is actually driver, it has got one broken teeth. Pinion D and pinion F are defective. Here actually consider the case, in the case of pinion the defect is due to a single teeth broken, okay, and in case of drafting roller its defect is due to the eccentricity of the drafting roller. The values in the parenthesis, these are either diameter or number of teeth. Okay. Now, we have to calculate. Now, try to see, this is the situation. Now, first condition is that the pinion D is defective. So, this is the pinion D. Now, let us see, the pinion D is rotating, it is a driven. So, once and it has got one defect, one teeth actually broken. Here as it is a driver, so this will give drive to the back roller and middle roller, but this teeth will not affect, broken teeth will not affect the motion of the back roller and middle roller, because they are rotating. Okay. They are basically it is getting drive, it is getting drive from somewhere else, but the roller which will get affected, which will get jerky motion is that it is a C roller, okay, roller C, which is actually driven by D. So, that means one rotation of roller D will give one jerky motion of C, on C, and then it will get, that jerk will get transmitted to roller B and then roller A, and from roller A only to front roller. So, that after certain interval the front roller will rotate little bit in, will give some jerky motion, but once the defective teeth is coming, then only it will get jerky motion, otherwise there will not be any such, it will be smooth rotation. So, what we have to calculate, for one rotation of this roller D, what is the delivery by the front roller, and that will be the effective wavelength. So, for one revolution of D, the front roller will rotate 90 is the, this is the teeth, number of teeth, and by 121, 90 by 121, this is a driven driver, all the drivers are 90 and 121 they are driver, and driven is 30 and 11. So, this is the 33 revolution will be there. For one revolution of D, the front roller will rotate 33 revolution, and the front roller delivery will be the, if we know the diameter is 25.4 millimeter, it is 2.63 meter. So, we will see if the roller D is defective, the pinion D is defective, then it will create, it will generate one periodic fault in the spectrogram, will show up one actually defect at 2.3 meter, that we can calculate. This is, and if the roller F, there is any defect in F, then one revolution of F, the middle roller will rotate by one revolution again, because it is a 26 and 26, F and G are same teeth. So, the middle roller will rotate by one revolution, and then it will generate one defect of the value which is equal to the wavelength will be equal to the circumference of the middle roller. So, that at the middle roller stage it will create one defect which is actually the periodic defect, which with the periodicity that wavelength will be pi and the circumference of the multiplied by 23 in terms of millimeter. Now, once it is generated here at the middle roller, then at this is the break draft zone and the main draft zone. After generating, this will get stressed because it will get drafted and that draft will stress the wavelength and we will get final wavelength. So, middle roller revolution is that middle roller delivery per revolution. So, per revolution this is pi d, that means its circumference is 7.23. For one revolution it is giving this much material to 7.23 centimeter material, and it's basically in front draft is we can calculate the front draft. If we know the we have the data, this is the yarn count and sliver count is known, this is and the back zone drafting is known. So, we can calculate this is the front zone draft. So, 29.6 is the front zone draft, and if we multiply because it will be stressed by 29.6 times. So, if we multiply the 7.23 into 29.6, so it is coming out to be 2.14 meter. So, if there is any problem in front zone, so if roller F, it will create one periodic fault of that wavelength 2.14 meter. So, in this way we can calculate, if we can go in the backward also. If we know the from the spectrogram, if we know this the wavelength of the periodic fault, then what we can do? We can go stepwise backward and accordingly we identify the faulty roller. Okay. Our next problem is like this: we know the defect, length of defect, periodicity of the defect, and we will try to identify the defective portion. Okay. And here this is the situation. In this numerical, what it is given, its yarn is given, yarn is tested, a yarn of 14.7 tex ring spun yarn was tested and found that to have a periodic fault of length 57.7 meter. So, that in the spectrogram it shows that at 57.7 meter there is a hump, okay, chimney is formed. So, that identifies, and it has been actually identified that it is a real fault, real periodic fault, and the system is that total draft in the draw frame, roving frame and ring frame. So, the system is the draft, draw frame, roving frame and ring frame. It is known, it is 6, 10.5 and 25. 25 draft is given in the ring frame, okay, respectively, and the roller size and draft distribution in the draw frame are giving like this. So, it is a back roller, third roller, and it is a actually 4/4 drafting system. So, back roller, third roller, second roller, front roller, and after that calendar roller. Now, the fault can occur at any point, maybe in ring frame, maybe in roving frame, or maybe in draw frame. So, first we have to identify the which machine is responsible. Okay, we will go step by step. Now, the periodic length is its length of the yarn is the 57.7 meter, that it is given, and total draft in ring frame is 25. Now, 57.7 meter length in ring frame it cannot occur, because ring frame, if we see the total draft and total circumference of the rollers, it cannot match, because it will be much less than that in ring frame, much less than that, it will be below 1 meter sometime, but that we can always check, and but few meter, but it will not be definitely 57 meter. Okay. Now, then we have to take care of the, we have to see the backward portion. So, in backward next portion, next machine was that it is a roving frame. If the roving frame has got its problem, then the what will be the in the roving, what was the periodicity? The in roving frame, in roving the periodicity was 57.7 meter divided by 25, because 25 times it is stressed. So, periodic wavelength of roving will be 2.308 meter, that is also very long for roving, because in roving we give draft only up to maximum 10 draft. So, that it's basically that has been, you can we can always check with the roving frame the diameter of the rollers and the distribution of the draft, and it is not there. So, then we will go further backward. So, then we have to see the draw frame. Now, if we see the draw frame, if we want to see the, that means the output of the draw frame, that means draw frame sliver will have the periodicity of length will be, the total draft in roving is 10.5. So, draw frame sliver will have periodicity is 57 divided by 25, that is 2.38308 divided by 10.5. So, it is coming out to be 22.2198 millimeter. 0.2198 millimeter, sorry, meter means it is a 219.8 millimeter. Now, we have to actually match this wavelength. So, this sliver has got wavelength of periodic wavelength of 219 millimeter. Okay. The periodic wavelength of draw frame sliver is 219.8 millimeter, and diameter of calendar roller as it is given, it is a 50 millimeter diameter. This calendar roller has got 50 millimeter diameter. Suppose we assume the calendar roller is now defective. Now, it has been, now we have identified that the ring frame is not culprit, the roving frame is not the culprit, the draw frame where it the periodicity has generated. Now, we have to identify among all these rollers 1, 2, 3, 4, 5 sets of rollers, which roller is problematic, and if there is any problem in the calendar roller, then this distance. Now, let us see, assume that there is a problem in calendar roller. Calendar roller is eccentric or it is moving erratically. In that case, the diameter of calendar roller is given and its circumference will be pi 50, it will be 157.06 millimeter. So, that means the wavelength is more than this circumference, that means the calendar roller is not the it is not generating the defect. Okay. So, not matching with the wavelength of the sliver. Okay. The wavelength is more than that. If once the wavelength is more than the particular portion, particular location, then we have to, the technique is we have to go back. So, now let us go the next backward component, which is the front roller F. Draft between, now draft between front roller and calendar roller, that is given, it is a 1.01, it is the draft between that. So, this wavelength we now divide by 1.02 to get the wavelength generated by the front roller. The material which is coming out from front roller will have wavelength of 215.5 millimeter. So, periodic wavelength after f will be 215.5 millimeter. So, now again we will now check whether the front roller there is any problem or not. So, wavelength of the after front roller is 215 millimeter and diameter of front roller is given, it is a 32 millimeter diameter is given, and then circumference of front roller we can calculate is 100.53. Okay. Still the wavelength is more than the circumference of that front roller f. So, that means front roller is not actually generating the fault. So, not matching with the wavelength after front roller, that is wavelength is more. Then what we have to do? We have to go back to the next roller, which is second roller. So, draft between front roller, second roller and front roller, which is main zone draft, that we can calculate by knowing other draft. So, 6 is the total draft in the system, and back zone draft, middle zone draft, and then the calendar zone draft. If we divide, then we will get 2.75. So, 2.75 is the draft between second roller and front roller, which is front zone draft, that we have calculated. 1.02 is the draft which is given in the table here, 1.86 draft is given here, and 1.15 draft is given in the front. This was not given, but total draft was given as 6. So, we have calculated this draft as 2.75 draft. Now, we can just divide this 15.5 by 2.75, which is actually the which will give the periodicity of wavelength after second roller. After second roller, the periodicity will be 78.4 millimeter. The periodicity of after the second roller, it is a 78.4 millimeter, and if we see the circumference of second roller with a diameter of 25 millimeter, it comes exactly same as 78.5 millimeter. It is matching with this value. That means, the fault is generated by the second bottom roller. This roller is defective, okay, matching with the wavelength after second roller, and conclusion is that second roller is faulty, that is there is eccentricity in second roller. Now, in industry what they do, they create charts of different roller, different gear, and accordingly what will be, if the yarn is there, yarn spectrogram shows particular defect, say at defect say 57.7 meter, this particular roller will be responsible. So, they have the total chart, and immediately they do not need to calculate in this way, but once they have to calculate, and but the new modern machinery manufacturer, they show they have the total data, they show they give all the data that the for a particular defective machine component what will be the effective wavelength of periodicity, that one can immediately locate. Okay. Now, we must know this system. then we can actually solve the problem, because in industry we impart different types of drafts. So, for different draft we must know the basics of how to analyze the spectrogram. Okay. Now, we will discuss another important part, which is called variance length curve. Okay. Variance length curve is a very important. It has got two types of variance length curves. Now, this is a yarn. Okay. With a certain variation. Now, it has got two types of curves. One is called between length variation. Now, between length means the yarn is there, as we have seen in capacitance type tester, we have the data of in each and individual point. Okay. Now, if we cut the length, suppose we are cutting the length of certain, this is the length. We can cut this length, this is L, or we can reduce the length. Now, if we say start with a least length, ideally we see say 0 length or very small length, we are cutting the yarn with a very small length. This is the cut length. Now, if we test, if we take the mass, so imagine we are taking a mass of say very say delta L length, very small length. So, it will give a mass of W 1, W 2, W 3, W 4. So, it will take care of mass, wide variation of mass. So, here it is a W something. So, lowest mass to maximum mass, because here our cut length. So, the material, say this yarn is there, this yarn we are cutting with a very small length, say in the micro level we are cutting that length, and we are taking the mass, physically we are taking the mass. In that case, if we see the variation what we will get, the CV percent and square of CV percent if we measure, it is a variance. Variance if we measure, it will be maximum with the, this is the cut length. At smallest cut length, the variance will be maximum. Now, suppose what we do, we increase the cut length, we are increasing the cut length, this is the cut length. Again we are taking another cut length, another same cut length, we are cutting and weighing mass, taking the mass. If we once we increase the cut length, what will happen? This internal variation in the mass per unit length will get averaged out. We will get a value m 1, here we will get value m 2, here we will get value m 3, like this. This m 1 takes care of all this variation, it is average of this, and then if we take the CV percent and the variance, we will get certain variance which will be much less than this variance. And if we increase the cut length further, we will get the lower and lower value of variance. So, that means, if our cut length is small, then we are actually, and then we are measuring the CV percent between this length, between these masses. That is why it is called the CV between length or variance between length, and which reduces logarithmically with the increase in cut length. Here x axis is cut length. Now, considering another situation, this is called between length, means between small length. This is one was this length which was giving highest value, one another was this cut length, longer cut length, it was giving this value, another was between this cut length much longer, this was giving this value. So, you take mass and then calculate CV, calculate variance, you are getting this. Take mass, calculate CV, calculate variance and plot this. So, if we keep on increasing the cut length, we will get the lower and lower variance value. Another type of curve which is known as within variation. Within variation means, see what we are doing, we are taking cut length of very small length, very small length. Now, imagine if we are taking very small cut length, in that case the variation will not be there. If we are taking very small piece of yarn and imagine we are trying to measure the variation within that. So, if I have a very small yarn and I do not have anything, I am not comparing with anything, I am only measuring this portion, variance of this portion only by some imaginary mean. I am measuring the variance only of this portion, rest yarns are not there. So, variance within that yarn, if the cut length is very small, the variance will be almost 0. There is no imaginary, if the cut length is 0, the variance will not be there. If we increase the cut length little bit, variance will get little bit high, because what we are talking the variance within that length. Suppose we have taken cut length of up to this point. So, it is taking care of variance of within this up to from this point to this point variance. So, the variance will increase little bit. If we take cut length of this, it will take variance from this point to this point also, the variance will increase. This is called VL curve. So, variance within length. Okay. So, variance between length, mass of each length L is measured and CV is calculated. Okay. L varies subsequently and then the CV is the CV between the L length and giving the symbol CBL, and if we take the square of that variance, it is a BL curve. Okay. The nature is the logarithmic nature, it is the that is this is the nature. Okay. Now, the next curve is that it is a within, as I have already mentioned, with the increase in cut length, the within length variation will increase, and the nature of curve is again logarithmic curve, this is the curve. Now, the total variation, total variance is the summation of BL and VL, it is just its opposite. So, if we want to take the variance, total variance, it is the summation of BL and VL. So, in this BL or VL curve, it shows a nature of the variation, and also from BL curve we can get the idea about periodic variation, at which portion suddenly there is an increase. Suppose the curve in this BL curve, in this portion there is certain increase in variance. Ideally this curve should be like this, okay, logarithmic curve. Suppose it is not that smooth, suddenly we have found there is certain increase in variance here at this zone. That means that is the zone where periodicity is occurring, and it gives higher values of that evenness, okay, unevenness CV percent. And this also in if we do not have the spectrogram, the variance length curve also give idea about the periodicity, the where the periodic faults are occurring. Okay. And based on this we will try to solve a numerical which is simple by, but we will try to solve, but that we will do in the next class. Okay. Thank you.